Hi, this is Group 2209, and our group focuses on electric machine voltage insulation system. And our members include Evan, me, Rowan, Drew, Edith. And our sponsor is Electric Bolt, and our advisor is Professor Cal. Project focuses on insulation for electric motors because it has effect on motors' size, weight, cost, machine longevity, and motors' thermal performance. And our primary objective is to focus on the newly developed nanostructure insulation by the econ researchers, with hopes that it will provide more benefits to electric machinery, more specifically electric motors, than the current industry standard insulation. And our project focuses on design and testing for motors. So we have to learn about the programs used for motor design, motor simulation, and thermal simulation for the motors. And second, we have to uh, design and model different marine propulsion motors and compare their thermal performance. And while using the nanostructure insulator and the tape insulator. And lastly, we'll have to apply one cooling method for each of the models, so they can replicate real life thermal performance for the models.
Our approach to the project, a nearly identical project, was done by Yukon researchers. In that project, two medium voltage induction motors are modeled and simulated for thermal performances. One motor used the new nanostructured insulation and the other used the industry standard mica tape insulation. We have been replicating the work that they did to learn the software and ensure that we get accurate results. Programs used ANSYS. The first program we used was RM Expert. It was used to generate basic motor models based on desired parameters. The second program used was Maxwell 2D. It was used for motor EM simulations and adding insulation into the model. The third program was Steady State Thermal. It took the 2D motor model and EM simulation data to perform thermal analysis.
To create the initial model of the motor, we used the RM Expert software. By inputting the given parameters seen in the table on the right, we were able to generate this accurate 2D model of the motor. From here, we transferred that RM Expert model into the ANSYS Maxwell 2D software. This software allows us to run EM simulations on the motor and make adjustments to it. We were able to manually add in the insulation wedges and spacers to the stator coils within this software using the material data that was given to us. Still within the Maxwell program, motor losses were then calculated through simulations. We found that these losses were nearly identical to the desired results, meaning that our model and simulation process was correct. These motor losses are important for our project because they're needed for thermal testing. Using ANSYS Workbench software, our Maxwell 2D motor model and simulation results are linked into a thermal program, allowing us to do multiphysics analysis. Once everything is imported properly, the given thermal boundary conditions are applied, and we can run the simulations. The final result is the thermal distribution of the motor when one of the insulation types is applied.
One of the motors we're supposed to model after is the AziPod XO2300 propulsion motor. This specific motor was a three-phase synchronous motor and was rated with a power of 22 megawatts at a propeller speed of 155 RPMs and a supply voltage of 3 kilovolts. Our first design tried to focus on being a synchronous design. We ran into some issues with this, so we decided to opt for an induction design. The image to the left is one of our older induction designs. It was not capable of meeting the 23 megawatt spec of the AziPod 2300 motor, but as you can see in our induction motor design on the right, this was capable of doing that while also meeting the propeller speed. Our design on the right was also capable of putting out more torque than our old design.
There are three cooling methods for motor designs, and which are direct liquid cooling, indirect liquid cooling, and air cooling. We'll be using indirect liquid cooling because it is easier to implement on the motor models, and also provides more cooling and thermal control for the motors than air cooling.